What if you could step into a machine and travel across time, witnessing the rise and fall of civilizations, meeting historical figures, or even seeing the distant future where humanity colonizes other planets? Time travel has long been a captivating idea in both science fiction and philosophical debates. From H.G. Wells' The Time Machine to Christopher Nolan's Interstellar, the concept of manipulating time has thrilled audiences worldwide. But beyond fiction, scientists have spent decades investigating whether time travel is theoretically possible. Could modern physics hold the key to making this dream a reality? Or are we forever bound by the relentless march of time? To truly understand the possibility of time travel, we must first unravel the nature of time itself. In our everyday lives, time appears to move in one direction, forward. Seconds turn into minutes, minutes into hours, and the past seems permanently out of reach. But physics tells a different story. According to Albert Einstein's groundbreaking theory of relativity, time is not an absolute constant. It can stretch, compress, and even move at different speeds depending on gravity and velocity. This discovery opened the doors to the idea that time could be traversed, at least in some theoretical sense. But while time travel to the future has already been scientifically observed on small scales, traveling to the past presents a far greater challenge, one riddled with paradoxes and theoretical roadblocks. In this video, we'll explore the science behind time travel and examine whether it is fact or fiction. We'll break down the concepts of relativity, time dilation, wormholes, quantum mechanics, and the paradoxes that could make traveling to the past impossible. Could Einstein's equations hold the secret to bending time? Do wormholes exist, waiting to be unlocked? Or is time travel nothing more than an illusion created by the limits of human perception? Stay with us as we dive deep into the fascinating and mind-bending world of time travel. For centuries, time was thought to be an unchanging, universal constant, ticking forward at the same rate for everyone, everywhere. This idea was deeply rooted in classical physics, where time was seen as a separate entity from space, moving independently like an unstoppable river. Sir Isaac Newton, one of the greatest minds in history, believed that time flowed uniformly, unaffected by external forces. However, this view of time began to change in the early 20th century, when Albert Einstein introduced his groundbreaking theory of relativity, which forever altered our understanding of time and space. Einstein's work showed that time is not an independent force but rather a dimension woven into the fabric of reality, much like the three spatial dimensions we experience. He proposed that space and time form a single continuum called space-time, which can be warped and stretched by gravity and motion. This means that time does not pass the same way for everyone. It can slow down or speed up depending on how fast an object is moving and how strong the gravitational field around it is. This revolutionary idea shattered the notion of absolute time and laid the foundation for modern discussions on time travel. One of the most famous consequences of Einstein's theory is time dilation, which occurs when an object moves at speeds close to the speed of light. According to Einstein's special theory of relativity, the faster an object moves, the slower time flows for it relative to an observer at rest. This has been experimentally proven through high-precision atomic clocks placed on fast-moving aircraft and satellites. Clocks on these objects tick slightly slower compared to those on Earth, meaning that astronauts aboard the International Space Station technically age a tiny bit less than people on the planet's surface. While this effect is minuscule at current speeds, it suggests that traveling far into the future is theoretically possible if one could approach the speed of light. Einstein's general theory of relativity expands on this concept by introducing the effect of gravity on time. He demonstrated that massive objects like planets, stars, and black holes create gravitational time dilation, meaning that time moves slower in stronger gravitational fields. A famous example of this can be seen in the movie Interstellar, where astronauts experience time at a much slower rate near a massive black hole. This phenomenon has been confirmed by experiments on Earth, where clocks positioned at higher altitudes, experiencing weaker gravity, tick slightly faster than those closer to sea level. This discovery suggests that traveling to areas of extreme gravity could theoretically allow someone to experience time differently than those further away from such forces. Another intriguing implication of Einstein's work is the possibility of closed, time-like curves, which could allow for time loops or even backward time travel under specific conditions. These curves, predicted by general relativity, suggest that under certain space-time configurations, a path through space could loop back on itself in time. Some theoretical solutions, such as the Gödel universe, propose that a rotating universe could create such closed loops, though current observations indicate our universe does not rotate in this way. While these ideas remain speculative, they provide a fascinating glimpse into how the structure of space-time could, in theory, permit time travel under the right conditions. A related concept is the existence of wormholes, also known as Einstein-Rosen bridges. These are hypothetical tunnels that connect two different points in space-time, potentially allowing for instantaneous travel between distant locations, or even different time periods. If a stable, traversable wormhole could be created, one end could theoretically be placed near a strong gravitational field, while the other remains stationary, creating a time difference between the two openings. However, no natural wormholes have been discovered, and the extreme conditions required to keep them open, such as negative energy, make their existence highly uncertain. Nevertheless, they remain one of the most popular and scientifically intriguing ideas for time travel. Despite these fascinating theories, the nature of time remains one of the greatest mysteries in physics. While Einstein's work suggests that time is malleable and interconnected with space, we still lack a complete understanding of its true nature. Some physicists believe that time is an emergent property rather than a fundamental aspect of reality, meaning it could be an illusion created by deeper quantum processes. Others propose that time may exist in multiple dimensions beyond our perception, potentially allowing for hidden pathways through the past and future. As scientific research advances, our grasp of time's true nature may evolve, bringing us closer to answering the age-old question: is time travel truly possible, or will it forever remain a product of human imagination? Time travel to the future is not just a theory, it is a scientifically proven phenomenon. According to Einstein's theory of relativity, time is not absolute but relative, meaning it moves at different rates depending on the speed at which an object is traveling and the gravitational forces acting upon it. This is known as time dilation, and it has been demonstrated in numerous experiments. The faster an object moves, the slower time passes for it relative to someone who is stationary. This means that if we could travel at near light speeds, we could leap far into the future while barely aging ourselves. While we may not have the technology to reach such speeds yet, the physics behind it is well established. One of the most famous demonstrations of time dilation comes from experiments with atomic clocks. Scientists placed one highly precise atomic clock on a high-speed airplane while keeping another identical clock on the ground. When the airplane landed, the airborne clock had recorded slightly less time than the clock that remained stationary, confirming Einstein's predictions. Although the time difference was just a few nanoseconds, the effect would be much greater at speeds approaching the speed of light. This means that an astronaut traveling at near light speed for what seems like a few months could return to Earth to find that centuries have passed. This concept is sometimes referred to as the twin paradox. If one twin remains on Earth while the other travels at high speed through space, the traveling twin would return much younger than their sibling. Another way to achieve time travel into the future is by harnessing the effects of gravity. Einstein's general theory of relativity states that time runs slower in stronger gravitational fields. This phenomenon, known as gravitational time dilation, has been observed in places with high gravity, such as near black holes. A famous example of this was depicted in Interstellar, where astronauts landed on a planet orbiting a supermassive black hole. Due to the intense gravity, time moved much slower for them than for those further away, meaning 1 hour on the planet equaled 7 years outside of its gravitational influence. While this was an extreme example, it was rooted in real physics. If we could position a spacecraft near a strong gravitational field without being destroyed by it, astronauts aboard could experience significantly slower time relative to Earth, effectively allowing them to travel into the future. Space agencies like NASA have already observed time dilation effects on astronauts aboard the International Space Station. Because the ISS orbits Earth at around 28,000 kilometers per hour, astronauts experience time slightly differently than people on the planet's surface. Over the course of a 6-month mission, an astronaut may age a few milliseconds less than someone on Earth. This means that, in a very real way, astronauts are already traveling into the future, even if only by tiny fractions of a second. The effect becomes far more significant at speeds closer to the speed of light, which is why many scientists believe that future space missions could push the boundaries of time travel even further. If humans ever develop technology that allows us to travel at a substantial fraction of the speed of light, we could theoretically make long jumps into the future. For example, if a spaceship could travel at 99.999% the speed of light, a trip that seems like just a few weeks to the astronauts on board could result in thousands of years passing on Earth. This idea presents intriguing possibilities. Could future generations of astronauts venture into deep space, only to return and find a completely transformed civilization? This concept, known as time dilation-based future travel, is not just science fiction, but a mathematically sound prediction of relativity. While time travel to the future is possible, there are significant technological barriers that prevent us from achieving it on a large scale. For one, traveling at near light speeds requires an enormous amount of energy, far more than anything we can currently produce. Additionally, the human body may not withstand the intense forces involved in such travel, meaning that advanced shielding and life support systems would be necessary. Furthermore, even if we could travel into the distant future, there would be no way to return, a one-way trip with no possibility of going back in time. This raises profound philosophical and ethical questions about what it would mean for a person to leave their time period forever. Despite these challenges, the fact remains that future time travel is a proven reality. It's just a matter of scale. The next step for humanity is to develop faster spacecraft, better propulsion systems, and deeper understanding of gravity's effects on time. If we can overcome these challenges, it's entirely possible that future astronauts could travel thousands of years ahead, witnessing a world unrecognizable to us today. While true time machines may still be confined to science fiction, physics tells us that stepping into the future is not just possible, it is inevitable. While time travel to the future is a scientifically accepted reality, traveling to the past is an entirely different challenge. The laws of physics allow for forward time travel through time dilation, but backward time travel introduces profound paradoxes and theoretical complications. Many physicists argue that nature itself may prevent such a possibility, yet several intriguing ideas suggest that traveling to the past might not be entirely impossible. These theories are rooted in Einstein's general relativity, wormholes, closed time-like curves, and quantum mechanics, all of which present tantalizing but highly speculative avenues for backward time travel. One of the most well-known ideas for past-directed time travel involves wormholes, also known as Einstein-Rosen bridges. These theoretical structures are shortcuts through space-time, potentially allowing travel between distant points in space or even different times. According to Einstein's equations, wormholes could exist naturally in the universe, but they would be highly unstable. The moment any matter or even light entered a wormhole, it would collapse almost instantly. Some physicists propose that an exotic form of matter with negative energy, called exotic matter, might stabilize a wormhole, preventing it from collapsing and allowing it to function as a true time machine. However, such matter has never been observed, and even if it exists, we have no known way of harnessing it. Another fascinating concept is the idea of closed time-like curves, CTCs, proposed by Austrian physicist Kurt Gödel in 1949. Gödel discovered that if the universe were rotating in a certain way, it could theoretically allow an object to travel along a circular path in spacetime, eventually returning to its own past. While our universe does not appear to have the necessary rotational properties, Gödel's work opened the door to the possibility that spacetime itself could be manipulated to allow time loops. Other physicists, such as Frank Tipler, later expanded on this idea with the Tipler cylinder, a hypothetical structure involving an infinitely long, rotating cylinder that could, in theory, enable time travel to the past. However, this concept also faces major hurdles, as it requires infinite mass and energy, making it impractical. Even if a method for backward time travel were found, it would immediately raise severe logical paradoxes. The most famous of these is the grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, you would never be born. But if you were never born, then how could you have traveled back in time in the first place? This contradiction suggests that changing the past might be impossible, or that time travel would be constrained in a way that prevents any alterations to history. Some scientists propose the Novikov self-consistency principle, which argues that any events that occur in the past must be consistent with history, meaning that anything a time traveler does has already been accounted for and cannot change the outcome. A different approach to avoiding paradoxes comes from the many worlds interpretation of quantum mechanics. This theory suggests that each decision or event creates a new parallel universe, meaning that if you traveled back in time and altered the past, you would not be affecting your own timeline, but rather creating an entirely new branch of reality. In this case, rather than erasing yourself from existence, you would simply be shifting into a different version of history. While this idea is exciting, it remains purely theoretical and has not been experimentally verified. It also raises new questions about the nature of reality and whether infinite versions of the universe exist. Some scientists have explored the possibility that backward time travel could occur naturally through black holes or cosmic strings, infinitely long, narrow energy defects in spacetime. These structures, if they exist, could create massive gravitational forces capable of warping time in extreme ways. Some physicists, such as Stephen Hawking, speculated that a civilization far more advanced than ours might find a way to exploit these cosmic phenomena for time travel. However, Hawking was also skeptical of the practicality of such travel, famously proposing the chronology protection conjecture, which suggests that the fundamental laws of physics might prevent time travel to the past by destroying any time machine the moment it is created. Despite these theoretical possibilities, there is currently no experimental evidence to support the idea that backward time travel is achievable. Every attempt to formulate a practical method for time travel to the past encounters insurmountable energy requirements, paradoxes, and instability issues. Even if wormholes or closed time-like curves could exist, we lack the technology to manipulate them in a way that would allow controlled travel to the past. Moreover, the absence of time travelers from the future in our present era raises the question, if time travel to the past is possible, why haven't we seen visitors from the future? Some argue that time machines, if they ever exist, may only allow travel back to the point of their creation, meaning that we wouldn't see time travelers until the first functioning time machine is built. While the dream of traveling to the past remains one of humanity's greatest fascinations, the challenges posed by physics make it one of the most difficult problems to solve. Though we have plausible theories, none have been experimentally verified, and all face major scientific roadblocks. However, science is constantly evolving, and new discoveries in quantum mechanics, space-time physics, and energy manipulation could one day reveal new pathways to unlocking time travel. Until then, the past remains an unreachable mystery, at least for now. While Einstein's theory of relativity provides a framework for understanding time on a cosmic scale, the world of quantum mechanics introduces strange possibilities that could challenge our conventional understanding of time. Quantum mechanics governs the behavior of particles at the smallest scales, where reality becomes unpredictable and seemingly paradoxical. Some physicists believe that the quantum world may hold the key to time travel, offering insights that go beyond classical physics. Unlike relativity, which deals with space-time as a smooth fabric, quantum mechanics suggests that reality operates on uncertainty, probability, and entanglement, and these properties might allow time to function in ways we do not yet fully understand. One of the most intriguing quantum phenomena related to time travel is quantum superposition. In quantum mechanics, particles do not exist in a single definite state, but instead exist in multiple states simultaneously until they are observed. This is best illustrated by Schrödinger's famous thought experiment with a cat that is both alive and dead until someone opens the box and observes it. If particles can exist in multiple states at once, could time also exist in multiple states, allowing for movement between past, present, and future? Some researchers speculate that this could hint at a mechanism for time travel, though no practical method for harnessing this effect has been discovered. Another fascinating concept is quantum entanglement, where two or more particles become linked in such a way that the state of one instantaneously affects the state of the other, no matter how far apart they are. This effect, which Einstein famously called spooky action at a distance, suggests that information can be transmitted faster than light, an idea that seemingly violates relativity. Some physicists have wondered whether entanglement could be used to send information backward in time, potentially creating a form of quantum time travel. However, our current understanding of entanglement shows that while information between entangled particles is connected, it cannot be used to send messages into the past in any practical way. Perhaps the most controversial idea in quantum mechanics related to time travel is the delayed choice quantum eraser experiment. This experiment suggests that decisions made in the present can influence the past at a quantum level. In the experiment, particles exhibit wave-like or particle-like behavior depending on measurements taken after they have already passed through a system. This has led some to speculate that time, at least at the quantum level, may not flow strictly forward. While this does not directly demonstrate macroscopic time travel, it challenges our understanding of cause and effect, and suggests that time might be more flexible than we assume. The many worlds interpretation, often abbreviated as MWI, of quantum mechanics, offers another possible solution to the time travel paradoxes found in relativity. This theory suggests that every possible outcome of an event creates a separate, parallel universe. If true, then traveling to the past and making changes would not alter the original timeline, but instead create a new branching reality, allowing for a form of time travel without paradoxes. This interpretation could resolve problems like the grandfather paradox, where someone traveling to the past and preventing their own birth would simply create a new timeline where they were never born, while the original timeline remains unaffected. However, MWI remains purely theoretical, with no experimental proof that parallel universes exist or that humans could ever travel between them. One of the biggest challenges in connecting quantum mechanics to time travel is the lack of a unified theory of physics. Currently, general relativity, which governs large-scale cosmic structures, and quantum mechanics, which governs subatomic particles, are fundamentally incompatible. Scientists have long sought a theory of everything that could merge these two frameworks and potentially reveal deeper truths about time itself. Some theoretical models, such as loop quantum gravity and string theory, attempt to bridge this gap, but so far, none have provided definitive answers. If we ever develop a quantum theory of gravity, it may unlock new possibilities for manipulating time and even traveling through it. Despite its strange and counterintuitive implications, quantum mechanics offers some of the most promising pathways for understanding time travel. While no experiment has yet demonstrated the ability to send information or matter back in time in a controllable way, the unpredictable nature of quantum physics leaves the door open for future discoveries. As our understanding of quantum mechanics deepens, we may uncover hidden aspects of time that could revolutionize our perception of reality, and perhaps one day even make time travel a reality. Time travel has long been a subject of science fiction, but real-world scientific experiments have provided insights into the nature of time and whether time manipulation is possible. While no one has built a working time machine, several experiments have confirmed key aspects of relativity, quantum mechanics, and time dilation, phenomena that are essential for understanding the possibility of time travel. Current research continues to push the boundaries of physics, exploring whether the fabric of time can be bent, stretched, or even reversed under certain conditions. One of the most famous real-world experiments demonstrating time dilation is the Haffel-Keating experiment conducted in 1971. Physicists Joseph Haffel and Richard Keating placed 4 atomic clocks aboard commercial airliners and flew them around the world. When compared to identical atomic clocks on the ground, the airborne clocks had measurable differences in time due to their high velocity and altitude. This experiment provided strong evidence that time moves differently depending on speed and gravity, confirming Einstein's theory of relativity, and proving that time travel into the future is possible, at least on a small scale. Another major experiment that supports the effects of gravitational time dilation is the use of GPS satellites. These satellites orbit Earth at altitudes of about 20,200 kilometers, 12,550 miles, and move at speeds of nearly 14,000 kilometers per hour, 8,700 miles per hour. Due to both their speed and weaker gravitational field compared to Earth's surface, time moves slightly faster for GPS satellites than for people on the ground. If scientists didn't account for this time difference, approximately 38 microseconds per day, GPS systems would become inaccurate by several kilometers over time. This is a real-world application of time dilation and further proof that time travel into the future happens every day, even if only by tiny fractions of a second. Despite these promising experiments, major challenges remain. The energy requirements for manipulating time on a large scale are currently far beyond human capabilities, and many aspects of time travel remain purely theoretical. However, advancements in quantum computing, particle physics, and space exploration may bring new breakthroughs in the coming decades. As researchers continue to test the limits of physics, the dream of time travel, whether to the future or the past, may not be as far-fetched as it once seemed. Time travel has remained one of humanity's greatest fascinations, capturing the imagination of scientists, philosophers, and storytellers alike. From ancient myths about gods manipulating time to modern films portraying time machines, the concept has been deeply embedded in our culture. But beyond fiction, serious scientific inquiry has sought to determine whether time travel is physically possible. Through the lenses of relativity, quantum mechanics, and theoretical physics, we have explored various mechanisms that could, at least in theory, allow for movement through time. The reality, however, is far more complex than simple stories of jumping to the past or future. While time travel to the future has been scientifically demonstrated in small increments through time dilation, time travel to the past remains speculative, filled with paradoxes and unresolved mysteries. The question remains, is time travel destined to remain a fascinating dream, or could it one day become reality? The ability to travel into the future has already been proven beyond doubt through Einstein's theory of relativity. Time dilation, as observed in real-world experiments with GPS satellites, atomic clocks, and high-speed travel, shows that time slows down for objects moving at extreme speeds or experiencing intense gravitational forces. Astronauts aboard the International Space Station age fractions of a second slower than people on Earth due to their speed and the weaker gravitational field in space. This confirms that if we could reach speeds near the speed of light, time would slow down dramatically, effectively allowing a traveler to move far into the future while barely aging themselves. The biggest hurdle, however, is the technological limitation. Current space travel methods are nowhere near fast enough to achieve this effect on a meaningful scale. The energy required to propel a spacecraft to such extreme velocities is beyond our present-day capabilities, meaning that while the science of time travel to the future is solid, the engineering challenge remains immense. On the other hand, time travel to the past encounters far greater obstacles. Theoretical models such as wormholes, closed time-like curves, and rotating black holes suggest that space-time could theoretically be bent or looped in ways that permit backward time travel. However, none of these methods have been experimentally verified, and many require forms of exotic matter that have never been observed in nature. Additionally, even if time travel to the past were possible, it could lead to logical paradoxes, such as the famous grandfather paradox, where a traveler going back in time could alter history in ways that make their own existence impossible. Some physicists, like Stephen Hawking, have suggested that the laws of nature may impose a kind of chronology protection principle, preventing backward time travel from occurring naturally. Others argue that alternative solutions, such as the many worlds interpretation of quantum mechanics, might allow for backward time travel by creating new parallel universes rather than altering the existing timeline. Quantum mechanics provides some of the most intriguing possibilities for time travel. Unlike classical physics, which views time as a linear and unchangeable dimension, quantum physics suggests that time may be far more fluid and uncertain. Experiments such as the delayed choice quantum eraser indicate that quantum particles can behave as though future measurements influence past events, suggesting that time may not function the way we intuitively perceive it. Additionally, quantum entanglement, in which two particles remain connected across vast distances, has led some to speculate about the potential for information to travel backward in time. While these ideas are highly theoretical, they challenge our fundamental understanding of cause and effect, and hint at the possibility that time travel might not be as impossible as once believed. However, for now, no practical method for using quantum mechanics to send information, or people, through time has been discovered. Beyond theoretical physics, modern experiments and current research are actively exploring time travel-related phenomena. The Haffel-Keating experiment, which involved flying atomic clocks around the world to observe time dilation, confirmed that time moves differently depending on velocity and gravity. The LIGO Gravitational Wave Observatory has provided insights into how massive objects like colliding black holes can distort space-time, hinting at the possibility of creating extreme conditions that could manipulate time. Researchers have also investigated whether wormholes could exist in nature and, if so, whether they could be stabilized to allow for time travel. In 2022, a group of physicists used quantum computing to simulate a simplified version of a wormhole, though this was purely a mathematical exercise with no physical implications. While these experiments demonstrate that time behaves in ways we are only beginning to understand, none have yet provided concrete evidence that human time travel is achievable.